Hey everyone, welcome back to another Explainer. Today, we're diving into a literal scientific detective story. We're going to track down the massive, and I mean massive, amounts of invisible energy required to change the state of water. Have you ever actually stopped to wonder what's going on at the microscopic level when ice turns to water or when water flashes into steam? It's not just about the number on a thermometer changing, it's all about this hidden heat. So let's jump right in.
Quick look at our roadmap for today. We're going to start by uncovering that hidden heat, then establish our calorimeter baseline, move on to melting ice for the heat of fusion, and finally, we'll capture some steam to look at the heat of vaporization.
Okay, think about this for a second. When a piece of ice melts, the temperature sits right at 0 degrees Celsius until the very last solid crystal turns to liquid. You're constantly adding heat to it from the room, right? So where does all that energy actually go? Well, that is the invisible toll water pays to transform itself. We're going to frame our entire explainer today around solving this exact energetic mystery to show you how scientists track energy that you can't even see or feel.
Section 1. Uncovering hidden heat. Finding the invisible toll water pays to change states.
So, to solve this thermodynamics mystery, we really need to define what we're looking for. Enter the latent heat of fusion. Simply put, it's the exact amount of heat required to move exactly 1 kilogram of a substance from a solid state to a liquid state. This is our first fundamental concept. It's literally the raw energy that goes into breaking the physical bonds holding the solid ice together rather than just raising the actual temperature.
Now, on the completely opposite end of the spectrum, we've got the latent heat of vaporization. Broadly speaking, that's the massive amount of heat required to jump from a liquid to a gas. But here's what's really fascinating about our specific setup today. We're technically measuring the exact reverse. We're looking at the heat of liquefaction. When we pump hot steam into cooler water, it gets annealed, meaning it turns back into a liquid and releases all of its hidden energy. And the energy released by liquefying is exactly equal to the energy required to vaporize it, just, moving in the opposite direction. To actually track all this energy, we need a strict accounting ledger. The stars of our ledger are the latent heat variables for melting or liquefaction. We balance those against the heat involved in cooling the water already in our container, the heat lost or gained by the container itself, and the heat needed to warm up the newly melted ice. The crucial takeaway here is that this acts as a strict accounting system. In a perfectly insulated adiabatic system, the heat lost by the warm components exactly equals the heat gained by the cold components. You add up every single thermal transaction, and the whole shebang has to perfectly balance out to zero.
Moving to Section 2, the calorimeter baseline. Setting our energy trap.
Every detective needs a toolkit, right? We've got our standard lab gear. Thermometers, scales, flasks, heating plates. But the absolute star of the show here is the calorimeter. Think of the calorimeter as our ultimate energy trap. It's a highly insulated container designed specifically to stop heat from sneaking out into the room. This ensures that all thermal transactions happen exclusively inside, between the water, the ice, the steam, and the walls of the trap itself.
But there's a catch. The trap itself absorbs some heat, and we have to figure out exactly how much by calibrating it. We start with the precise amount of room temperature water inside the trap. Then we heat a completely separate batch to exactly 60 degrees Celsius. Now for the critical part. We quickly pour that hot water into the trap and shake it vigorously. Honestly, you have to be fast here to avoid losing heat to the air in the lab. Finally, we just wait for the hot and cold water to balance out and take that final equilibrium temperature. From this simple baseline, we know exactly how much energy our hardware absorbs.
Okay, Section 3. Melting ice, heat of fusion. Solving the solid-to-liquid mystery.
With our baseline set, we can finally investigate our first suspect, solid ice melting into liquid water. Look at this melting balance equation. We add up all the heat required to melt the ice and warm that new water, and we balance it directly against the heat lost by the room temperature water and the trap itself. Because the cold ice absorbs all the heat from the water and the container, the sum of all these energy transfers perfectly zeroes out. This beautifully simple balance is what lets us solve for that one unknown variable we've been hunting for, the hidden heat of fusion.
So how do we actually get the numbers to plug into that equation? In practice, we literally just drop a piece of 0-degree ice into our trap filled with a known volume of water. We seal it up tight, wait for everything to completely melt and balance out, and then record that final temperature. A quick measurement of the final water volume tells us exactly how much ice melted. These simple, practical actions give us absolutely every physical variable we need to solve the math.
All right, on to Section 4. Capturing steam. heat of vaporization, trapping the energy of a gas.
Let's contrast these two states for a second. For fusion, we just dropped cold ice into a trap. Pretty straightforward. But for vaporization, the game completely changes. We're looking at the transition between a liquid and a gas. To do this properly, we're actually going to force incredibly hot 100 degrees steam into our water trap to intentionally liquefy it. It's the exact same fundamental principle of balancing heat, just with way more energy involved.
As you can see with our setup here, we use a boiling flask sitting on a heating plate as a steam generator. As the water boils, that high-energy steam gets routed straight down a tube and injected right into our sealed water trap. We are literally pumping pure gaseous energy directly into the water, forcing it to violently condense and surrender all that hidden heat right inside our calorimeter.
Once again, pull out that strict accounting ledger. The vaporization balance equation functions on the exact same logic, and it's honestly incredibly cool when you think about it. All the heat from the steam violently condensing back to water, plus the cooling of that condensed steam down to the final temperature, plus the warming of the trap in its water, it all perfectly balances out to zero. The energy it gives off by liquefying is the exact identical massive amount of energy it originally took to boil it.
To execute this in the lab, though, we've got to be super precise because of how intense the energy is. We start with water in the trap, take the temperature, and begin boiling the water in our flask to pipe the steam in. But here's the key. We let the steam flow for exactly 5 minutes, and then immediately cut it off so we don't completely overwhelm the trap's capacity. We capture that final equilibrium temperature and measure the volume increase to find out exactly how much steam condensed. That final reading gives us the massive amount of hidden energy successfully captured in our system.
Now, I want to leave you with a provocative thought here. Think about the incredible amount of energy we just tracked in a few tiny milliliters of water. If a small laboratory calorimeter captures this much hidden energy during a simple phase change, how much invisible heat is continuously shifting around our entire planet every single day? Every time a massive glacier melts or the surface of the ocean evaporates into a storm system, staggering amounts of invisible thermal energy are being absorbed and released. The micromath we just did in our explainer lab today is the exact same math driving global thermodynamics and our entire climate system. It's a massive, invisible engine, and now you know exactly how to track it. Thanks for joining me on this deep dive into the hidden energies of our world. Catch you next time.